huge amount of new jargon that we create every single day. The problem with jargon is that a lot of the jargon leads to confusion. So the first question I want to try to answer today is why we have so much jargon. And I believe this happens for two reasons. The first one is we are addicted to complexity. We like complex projects. We like complex things. Probably the reason why we put a man on the moon before we added wheels to your language. If you go to Starbucks, you have small, instead of small, medium, and large, we have tall, grande, and venti. And this jargon really works because it looks sophisticated, but creates enough confusion that you have people going online and searching for the terms because they don't know, and you have websites that describe what are these copy sizes. The problem is, in the case of big data or artificial intelligence or machine learning, where you have much more complexity, well, the jargon generates much more confusion. So this desire to look sophisticated plus our addiction to complexity leads to jargon, jargon leads to confusion, that leads to hype. So what is big data? If you go to a lot of these conferences, you will have a lot of people talk about these 3 Bs or 4 Bs. These start by Doug Lane in 2001 from Gartner. He defined big data as velocity, variety, and volume. And we went from 3 Bs to 4 Bs to 5 Bs to 6 Bs to 7 Bs to 10 Bs. We are seeing an exponential growth of big data definitions, and all of them start with the letter B. And I'm not saying they're wrong. They definitely contribute to the jargon. They also miss the point. They add this too much complexity. Dan Ariely, who's a professor of behavioral economics at MIT, says this very clear, and I quote, "Big data is like teenage sex. Everyone talks about it, nobody really knows how to do it, everyone thinks everyone's doing it, so everybody claims they are doing it." At the end, we need to remember and understand that big data is just data. And the objective is to be able to solve problems with data. That's all that matters. Of course, we've been solving problems with data for centuries now. So, what is new now? If we want to understand what is big data, we need to understand what is new now. And a few things are different now. It's true, we are generating a huge amount of data. Every day we add 1.5 million times of all the content of the Library of Congress, every single day. On top of this, the cost of storing this data that has dramatically gone down. Today, with $1,400, you can buy enough storage to store every single book that was written in human history, something that would have cost you over $1 billion in 1984, something that will probably cost less than $100 in a few years from now. On top of this, the cost of the processing power that we need in order to process this data also has gone down. Your Xbox One at home has more processing power than a supercomputer that NSA bought in 1996 that cost $67 million, and we use this for gaming now. Well, this has, the fact that we can generate a huge amount of data, the fact that we can store this data in a very cheap way, and also process this data in a very cheap way, has enabled a lot of the new scenarios in machine learning or artificial intelligence. But we always need to remember that at the end, big data is just data. So I'm going to be talking about 6 different challenges that I see about the adoption of big data or AI. The first one is, we forget correlation doesn't imply causation. We forget that predictive power doesn't imply causation. So there's a few. If you take a look at ice cream sales and drownings are highly correlated. And this is not a spurious correlation. This is not a spurious correlation. There is a reason why this happens. This happens because there's a confounding variable that is temperature. Temperature goes up, more people buy ice cream, more people go to the beach, more drownings. But of course, if tomorrow I decide to ban ice cream sales, the only thing that will happen is that this correlation will break. Nothing else. There will still be the same amount of drownings. Unfortunately, majority of the people don't get this. Actually, Gallup did a survey a few years ago when they asked a very simple question. Do you believe correlation implies causation? 64% of Americans said yes. 28% said no, and 8% were undecided. And I'm not really worried about the undecided, I'm worried about the 64%. This is so prevalent that we see it in the news every single day. 2 years ago, Andrew Francis and Hugo Malone did a very interesting research paper. They found that there is a correlation between how much you spend in your wedding and the probability of divorce. But the paper is very clear that the only thing they claim is correlation and predictive power, nothing else. What did the newspaper report? Want a happy marriage, have a big cheap wedding. And it was not alone. They kill it for cheap wedding, for a marriage that lasts, try a big cheap wedding. This is exactly like saying, let's reduce drownings, let's ban ice cream sales. Exactly the same thing. The only newspaper that I could find that I got this right was Wall Street Journal. Will a cheap wedding help your marriage? A lesson in causation. So two lessons here. First one, correlation of predictive power does not imply causation, and majority of the people don't get this. Second one, machine learning can find patterns, but not necessarily will not prove causation. If we want to prove causation, we need to run a randomized control experiment. The output from a machine learning algorithm will just be something that implies predictive power, just correlation, or that's not necessarily causation. Challenge number two, human behavior can be a bad teacher. Majority of the time that we use machine learning models from data is usually something that we learn from human interactions. But we need to remember that not all human interactions is good. Not all human interactions is teaching us something that we should learn. UN Women, a few years ago, did a very interesting campaign showing on gender discrimination, showing real search engine auto-suggest and autocomplete. Auto-suggest is when you start typing in a search engine, it gives you a few options. Well, the problem is that this is something that, like the machine learning model, how it works is that it will learn from past behavior what we should show, given that what you have typed, what is the more probable phrase that the person is searching. The problem is it would show things that we should never show to our users. Again, the lesson here is if we're learning from humans, we have to be aware of things that we should avoid learning. We have to be careful what we learn. Challenge number three, machine learning can discriminate. Machine learning, from something that we're learning, from a feature space, machine learning we can measure only things that we call observable features, and will generalize based on those features. The problem is if we only judge people on the things that we can observe, and those features include gender, age, or ethnicity, machine learning can and will discriminate. Let me give you an example here. This is a real world example. This is a person that moved just a few feet away from his house to a new house in Chicago. He had so bad luck that he changed zip code. So instead of paying $269 in his car insurance, now he's paying $442. Why? Because the machine learning model is learning to generalize based on zip code. It doesn't know anything else. And at the zip code level, this is true. But that's a generalization. Economists call this statistical discrimination. Let me give you an example. Let's say you have a machine learning model that is trying to predict default rate. You have a loan application system and you need to try to understand default rate. If we know the disposable income of a person, it's very easy to predict the default rate. And if we know the disposable income of a person, the race is not predicted. The race doesn't have any predictive power. What's the problem here? Well, the problem is because disposable income has a different distribution by race, if we don't observe disposable income, that is usually the case, then race will have predictive power over default rate. But at that point, if we use race as a predictive power to default rate, we are discriminating on race. Something that is completely unfair, because if we observe disposable income, then race is independent. If you have 10 people that have the same disposable income, the default rate for those 10 people will be the same, independent of the race. But if we don't observe disposable income, then suddenly race has predictive power. At that point, you are discriminating. So if your model, you have features including gender, age, race, ethnicity, your machine learning model could be discriminating, and we need to be careful on this. Challenge number 4, we humans will try to game the system. There's a bar in Fremont in Seattle, and they came up with a brilliant idea that they wanted people to go there biking. And if you came biking, you will be part of the happy hour. But of course, they didn't observe whether the person was biking or not. They observed whether the person had a helmet. And having a helmet is correlated with biking. But this relationship is not causal, it's just a correlation. What happened? Well, people went there by car with a helmet, and they were part of the happy hour. Something that actually also applied to this case that is a little more problematic for society is that on May 6, 2010 at 2:45 p.m., market crashed 988 points. This was temporarily, the market lost $1 trillion. That's a lot of money. That's the same as the GDP of 93% of the countries on earth, including Switzerland. And at that point, they didn't know what happened, but they knew that something triggered the algorithm to start selling, and something triggered the algorithm to think that the market was crashing. Majority of the transactions in Wall Street today are done by algorithms. More than 80% of the transactions are done by algorithms. At that point, nobody understood what happened. They knew that whatever happened was tricking the system because the market recovered 2 years after that, 2 hours after that. So last year they found that Lavista Sarao, a UK trader from his home in London, that day he was spoofing the market. Spoofing is when you create a sell on a stock much cheaper to the actual market value, but then you cancel it to give the impression that the market is crashing, especially to the algorithms. So that day he made $200 million worth of bets that replaced and modified 90,000 times before they were cancelled. So of course, there was no cost for him. He was making these bets and then cancelling them. So we think today that this was probably the trigger, what triggered the whole market crash. That day he made almost $1 million worth of profit. The lesson here is that the relationship between the feature and the outcome that we have in our model is not causal, and the reason why people will try to game the system, we need to be careful because people will try to game the system, especially if there are some incentives for doing this. Challenge number 5, we can get fooled by bias. Let me show you what I call the left-handed dilemma. If the probability of being in this room today is independent of being left-handed, then the distribution of left-handed people in this room will be the same as the distribution of left-handed in population. 10% of you guys will be left-handed. Raise your hand if you're left-handed. Actually it works. Unfortunately, I have a very bad news for you left-handed people. In 1991, 2 researchers, Juan and Coren, did a very interesting study. They took a group of people that died and asked the family members whether they were left-handed or right-handed. What they discovered was very interesting and scary. Left-handed people would die 9 years younger than right-handed people. This research was published in the New England Journal of Medicine, that is one of the most prestigious medical journals we have. It was cited and referenced by many other researchers. It was even in the New York Times. If this was true, being left-handed was as bad as smoking 120 cigarettes per day. The good news for the left-handed people was that even though these researchers took a random sample of people, so they did the right thing, what they didn't consider was that for a long period of time there was a discrimination against left-handed people, and parents would force their kid to be right-handed. Eventually they realized that this was stupid, they stopped doing that, and this created an artificial increase in the left-handed population that gives the illusion, this bias gives the illusion that left-handed people die younger, when in reality it's not the case. The problem that I see is that whenever we start seeing fatal accidents by self-driving cars, people will think that because those statistics didn't apply to them, now the chances of having accidents are higher, and we will have a problem of adoption of this technology. Given that we have, as a society, we also need to consider that we will have fatal accidents done by cars. So, for example, we will need to consider if a self-driving car realizes that it will crash a crowd, what do we optimize? Do we optimize to saving the moral amount of people, or do we optimize to save the driver? These are important questions that we will need to answer because we will need to program them. Another question is, if a self-driving car crashes, who's liable? It's definitely probably not the driver. So the whole car insurance industry will need to change, and the laws will probably need to change. And we're probably 5 years away, so I think that we will solve the technology part before we solve a lot of these problems. Even after all these problems, even after all the concerns, the power of data is real. And there's a huge amount of problems out there that we can and we should solve with data. 40% of the food that we produce in the US today, 40% of the food goes wasted. 40% of the food. And this happens this is not only a $165 billion problem, this is also the single largest component of solid waste, and a huge amount of unused resources. And it happens for a reason. We can actually, if we have data, if we take a look at the food chain, during the food chain, we have people making predictions of how much they're going to buy, how much they're going to sell, and how much they're going to consume. If we have data, we can help solve some of these problems. If we have better models, we can solve some of these problems. In your smartphone today, you have more processing power than the one that was needed to put a man on the moon. We have the data. We no longer have excuses. Thank you very much.